Hello, this morning we're going to be investigating the gas laws. In particular, we're going to be investigating Boyle's law and Charles' law. So let's have a look at what those investigations will involve. So here is Boyle's law. Is that the pressure of an ideal gas multiplied by the volume of the ideal gas will be equal to a constant. As long as we have the same amount of gas, so that's the same number of molecules, same number of moles, same mass of gas, and as long as the temperature of the gas does not change. So in terms of variables, we could have the pressure as our independent variable. We can choose to change the pressure of a gas by squashing it and measuring the force we squash it with divided by the area over which the force is applied. And we can measure as our dependent variable V, the volume of the gas, making our control variables the temperature. And to keep that the same, we have to leave our gas to reach an equilibrium temperature after making any changes to its volume, and also the amount of gas. Now that's going to be tricky. The experiment we're going to do involves using a gas syringe, which I borrowed from the chemistry department. See, they do have a use. This gas syringe has been chosen because it's machined so that the size of this aperture and the size of the plunger match almost perfectly. The idea being that you could have a set volume of gas at atmospheric pressure, and then you can pinch off the end of this tube and apply a force to squash the gas down. Now, unfortunately, there will be some gas leakage from around the edge here, and there will be some gas leakage from around here. So in order to make sure we have a constant amount of gas, what we're going to do is set it up to the same initial volume each time we do a measurement, then pinch it, apply our force, make a measurement of the volume, then reset it back to the original volume with the end open again, seal it again, new force, measure the volume, release the force, open the end, reset the volume, and we'll have to do that over and over again. That way, any air that leaks in or out is going to be replaced. So how are we going to apply a known force? Well, we're going to use slotted masses and we're going to balance them on top. You'll see. So this is going to be our equation. We actually have atmospheric pressure plus this additional pressure. Let's call this delta P. That's going to be the total pressure, which multiplied by the volume is going to equal a constant. And we can use this experiment to measure atmospheric pressure. And it works a little bit like this. Our change in pressure, our extra bit of pressure, is going to be equal to the slotted masses that we stack up on top of the plunger, multiplied by the gravitational field strength. That will be equal to the force that's being applied, divided by the cross-sectional area of the plunger. And of course, the cross-sectional area of the plunger is a circular plunger, so that's going to be 1/4 multiplied by pi d squared. That's the usual equation that we use for the area. So our full equation becomes the air pressure, atmospheric pressure, which should be some sort of constant throughout the experiment, hopefully, if we do the experiment quickly enough, plus 4 times mg divided by pi d squared, all multiplied by v, is going to equal some constant. I'm just going to call it k today, like that. That's going to be our equation. Now we want to get this in the form y equals mx plus c. So to get it in the form y equals mx plus c, we need to consider what our variables are going to be. Well, m here is going to be a variable, and v we're going to measure as our variable. Everything else is a constant. So PA is a constant. What else is a constant? D is a constant. Obviously, G is a constant as well. K is a constant. There are lots of constants. So, and pi is a constant. I'm not even going to bother labeling that one constant. So we need to manipulate this equation, which is currently in some peculiar form like this, into the form variable equals constant times variable plus constant. So start off by multiplying out this bracket. So we end up with atmospheric pressure multiplied by the volume plus 4 pi, let's put g over d squared, because that's going to be a constant, multiplied by m and multiplied by v is going to be equal to k. Now that is currently in the form variable here, variable here, variable here, and everything else is constant. So it's not quite in the right form, but if I divide through by my volume, let's do that. Then I end up with PA plus 4g over pi d squared m is equal to k multiplied by 1 over v. And I've written it like that for a good reason that you'll see in a bit. We're getting closer, aren't we? Because look, there's our constant, there's our constant. Here's our variable, but we've also still got this pesky constant here. What a nuisance. But what we could do is divide through by k. Now, if we divide through by k, that's going to give us our equation in the correct form. So now 1 over v is going to equal 4g over pi d squared k m plus, and then it's 1 over k pa. Now we're in the correct form, aren't we? Because what we've got here is a variable. If volume is a variable, the 1 over v is a variable. We've got a variable here. The mass we're going to add is a variable. And over here, we've got this big dirty constant and this big dirty constant here. So we can plot our graph of 1 over v on the y-axis, m on the x-axis. The gradient will be this. But if we measure d and we know what g is, from the gradient we can determine k. And we'll use that value of k to determine atmospheric pressure from the y-intercept. So we multiply the y-intercept by k to calculate the atmospheric pressure. And that's something we can look up and check. So in terms of results, our results table is going to look a little bit like this. Our independent variable, which is the mass added, and that is going to be measured in, let's keep it in kilograms, lose everything in sensible units. And we're also going to have our volume of the gas, and that's going to be measured in, let's say, cubic meters. We might have to do some conversions along the way. We're then going to have 1 over v in cubic meters as our final column, which is what we're going to plot on the y-axis. So we're going to have 1, 2, 3, 4, 5, 6, a maximum of 7 data points. We still need to measure the diameter of our plunger and the mass of the plunger as well, because that will also be added to the atmospheric pressure. I mean, I don't think the mass of the plunger is going to be very much, but we absolutely should measure its mass as part of this experiment. Not quite enough room. We might only do 6 results. We'll see. We'll see if I've got enough room on the table. So there's my table drawn up. I need to make some measurements of D, and then I'm away. So let's start with that. D in, well, it should be in meters, but let's do this in millimeters, and I can convert it later, equals. So I've got a vernier caliper, and I'm going to use this to measure I can either measure the internal diameter of this aperture here, but it's curved at the edge. So I'm not sure that's going to quite work as I want it. It might work. I could measure the internal one there. But actually, I think it's going to be slightly more straightforward to measure the external diameter of this. So I'm going to pop that in there, and then I'm going to read it. I reckon that is 31.2. 31.2 millimeters. And I'm going to do this a few times just so that I can convince myself that it's the same thing. If it's not the same thing, I've got an uncertainty in this number then. And I'm not going to show you all of those measurements. There we go. So I've measured it 7 times. I'm now going to calculate the mean with this absolutely disgusting calculator. Oh, wish me luck. 31.2 times 1, 2, 3 plus 31.1 times 1, 2, 3, 4, and then divide all of that by 7. Ugh, yuck. 31 point. So this is going to be the mean D in millimeters is equal to 31 point. That's a big recurring number there. So let's record it to an extra couple of significant figures until I work out what the uncertainty is, which is highest minus lowest divided by 2. So that's 0.05. So 0.05. So I don't need that final digit there. So I can say 31.14 plus or minus 0.05. There it is. That is my mean diameter with the uncertainty. The unit is here. So now I've got the D, and I'm going to be squaring that later. G is 9.81. I'm going to take what I can look up, although I've actually measured it in a previous experiment, so I don't have to do that. K I need to measure, but we're going to do that with the data. So let's set up the experiment now. I almost forgot that I need to know the mass of the plunger, don't I? Let's turn this thing on. Oh, hurry up. There we go. 99.16. I'll do a bunch of these measurements. I misspoke before. It's 99.06, and every single one is coming out exactly the same. So, okay, it's going to be 99.06 grams. And I need to make sure I add that to every value in my mass added table. This should just fall down if there's, there we are, look. Ooh, just like that. So I'm going to have to add that to every single one of the values in my mass added table. It's just the way it is. Right, let's go with a volume of 100 milliliters. And that's our starting volume when the mass added is just 99.06. So I'm actually going to write that in straight away. 99.06 kilograms. I'm such a wally. Times 10 to the negative 3. Now it's in kilograms. In the table, you can't see what I've just done. Look at that. I've just written 99.06, but the unit was kilograms, so I've had to put that on the end. Not ideal, but never mind. And that's not one, I've done it again. Look, that's not 100 cubic meters. It's 100 cubic centimeters. So that is times 10 to the negative 9, I guess, times 10 to the negative centi, so 10 to the negative 6, times 10 to the negative 6 cubic meters. What a wally. Doesn't matter. I'll keep it with the standard form because actually that might make it easier a bit later on when I'm plotting graphs. We'll see. Right. Now what I'm going to do is try to work quickly. I need to put 100 gram mass on the top. Try not to let it slip off so that the chemistry department don't try and charge me for a new one of these. Fold this. This is much easier with 2 people. In fact, I'm not even going to clamp it. I'm just going to hold it. I'm going to fold it and hold it and see where it falls down to. Oh, do you know what? I've been an idiot, haven't I? Because that volume might not be right. I need to let go when it is... It's just a little bit under that, actually. I forgot. Such an idiot. So, where it says mass added, I have to let it fall to find out what the new volume is. So when there's no mass added, you can see I'm holding the mass up, which is just the plunger in this case. There's no mass on the top of it, as you can see. And I'm just holding the plunger. It's at 100. Let's turn this around so you can see it a bit more clearly. Turn this around. It's at 100 milliliters. So 100 cubic centimeters. Then I pinched off the end. I have to watch where it falls to. Actually, that's probably about right. It's not actually falling anywhere, is it? Maybe one milliliter it falls to the nearest. No, not even to the nearest milliliter notch. It doesn't fall that far. There's a lot of friction on this, isn't there? I'm going to go, look, that's just staying there. I'm going to go see if I can find a better one. Right, I'm back, and this one's got much less friction, but not only that, I have checked all the measurements, and they were close enough to the same that I'm not going to fuss about it. Plunger mass, 99.06, 96.94. Let me check it a few times. Yeah, that's the same. So 96 point, we've got 96.94. That's the only thing that's different, but the diameter is the same from what I can measure. Right, let's pop this in. Let's do this properly this time. When I just release the plunger, it falls. Clamp this better. Let gas in, lift it to there. I'm looking at this scale at eye level. I mean, you can actually watch it fall as the gas leaks out. Let's see if I can zoom in. You see, it is actually falling as the gas leaks out, slowly but surely. Now that's obviously no good. Right, so obviously this is going to be an issue. Yes, it is decreasing in volume when I release the plunger, but then it continues to decrease in volume. So I think I'm going to have to count that as no reduction in volume. That's the only thing I can sensibly call it. Right, let's set it back up again, add an extra 100 grams. So I'm going to write in my table 196.94. And I don't know why I'm writing this times 10 to the negative 3. I should have put that in the column header. So you see, the value of doing things in pencil means I could have rubbed out that 96.94. This, no one's going to be able to make sense of that. So I really should cross that out and write it again. 96.94 times 10 to the negative 3. That's a little bit better. And then here, I should have put this times 10 to the negative 3 up there. I should have done these in grams. But never mind. We're doing it now. So let's hold it up there. Place the 100 grams on the top. I'm still holding it. Pinch off the gas and see where it falls to before it starts slowly descending. I reckon that descended by 2 milliliters. Near enough 2 milliliters. I've done it a few times. I reckon that's 2 milliliters, which means the volume becomes 98 times 10 to the negative 6 cubic meters. Okay, now we're going to do it again. This time with 200 grams. So this is 296.94 times 10 to the negative 3. Every time I write that, I kick myself. Every time I have to write that bit on the end, I'm irritated that I hadn't planned ahead better with my table because it's not very neat. Right, 100, look at it at eye level, release. It's falling quite quickly now, which is making it quite difficult to judge where it falls to. I reckon that falls 3 milliliters. So that would be 97 times 10 to the negative 6. Let's go up a little bit more. Let's go to 400 added. And we're being careful. This should stay vertical. Otherwise, it's not going to be quite right. Because the force won't be vertically down on the plunger, which means it won't be as accurate as it should be. You can get plumb lines and stuff to measure it, but I'm not going to do that. Can't be bothered. Right, let's release it. Oh, it falls so fast. It's so difficult to get right. I think that is 5 milliliters it falls by. Yeah, oh, sugar. I hope that hasn't broken the bottom of it. No, it looks like it's all right. I think that was 5. So let's put that as 95 times 10 to the negative 6. Let's be careful not to just release the masses, otherwise I will shatter the bottom of this. That's why they don't let me use glassware, and why I have to borrow it from the chemistry department. Right, let's add another 200 grams. Just like that. And I would say, well, I'm not going to show you every measurement, but you know what? I might as well. There's no harm in it, is there? I should have put the cradle on the top. Right, so there's our 100 at eye level. It falls to about 7. Yeah, falls to about 7 before it starts slowly drifting down. So that was 696.94, and it falls to 7, so that'd be 93 times 10 to the negative 6. We're nearly there, just a couple more measurements. Might as well put these on the cradle so they're less likely to slip off. There we go. It's getting heavier and heavier. Looking at the eye level, it's on the 100. Holding it like this. Making sure it's vertical. Releasing it. Oh, that looks like it falls to about 8. Falls by at about 8. Let's try that again. 9 even. Let's try that again, because I think that was 9. You can actually do repeats. 8. I think that's either 8 or 9. I'm going to go with 9. So let's go with 91 times 10 to the negative 3. That's 8. 1, 2, 3, 4, 5, 6, 7, 8. That's 896.94 times 10 to the negative 3. And then I'm going to add 2 of these. I've only got 1 left. I'm going to add 1 of those on. I'm going to go in the prep room and get another one. So 996.94 times 10 to the negative 3. And let's find out, with 900 grams on, plus the 100 grams-ish of the plunger, which I might round to 100 grams to make it a little bit easier. Let's see what happens. Straight down to the 10, straight down to the 10 cubic milliliters, 10 milliliters. So that's going to be 90 times 10 to the negative 6. Right, I have all of my data. I'm now in a position to do the analysis. Rather bothersome. I've just realized that I wasn't recording audio, so I'm going to record this next bit again, even though I've done most of the work on this, but never mind. I had the data from the experiment. Then what did I do? I had to decide my axes and my scales. So I know I'm plotting 1 over v on the y-axis, and I'm plotting, let's get it like this, 1 over v on the y-axis and m on the x-axis. Now my m's, 96.94 grams, which is what 10 to the negative 3 kilograms was. In order to plot this, actually from 100 to 1000 fits perfectly across this x-axis. On that scale, each little square is worth 10 grams, which is, to the nearest 10 grams, this is 100. And even if I try to interpolate within that, it's closer to the 100 grams than it is the 90 grams. So there's no point me trying to interpolate even further within the fine grid points. So I just decided to call this 100, 200, 300, 500, 700, 900, and 1000. And I wrote those across there. Then I chose my y-axis scale. And I chose my y-axis scale using this. I thought, right, 10 times 10 to the 3, 10.1 to all the way up to 11.2 would give me a good range of data, and that's what I did along there. I didn't want to write 10100 because there wasn't a lot of room, which is why I did the 10 times 10 to the 3 along there. That's what that represents. Although I suppose actually that 10 to the 3 should have been down there, so maybe I should make that minus, but I always get sort of baffled with that. Let's leave it as it is. Then I did my line of best fit. Then I thought, right, error bars. And I know that each of these was give or take 1 cubic centimeter, 1 milliliter. So I took the worst case one, which is this one. And I said, okay, 1 milliliter divided by the 90 milliliters that it said gave me, there it is, 0.01. So that was, well, it's got a recurring dot, but that is, let's say, 1%, 1.1%. So I said 1% is the highest uncertainty, and so it's 1% of these, and from that I have done 1 small square all the way up. So that's why I've got the error bars to draw my worst acceptable line of best fit and my line of best fit. I'm now doing the gradient calculations. So I have my 11.09 minus 10.08. So that's 11.09, and down here 10.08. Let's See these two values there and there, which are on the line of best fit, which is slightly steeper, with the multipliers there. That's where I got to. I chose these points because they're where the grid lines cross nicely and conveniently, and I've used a horrible smudgy pen. So, we've all caught up, and I'm very irritated that I had to do that, but glad I noticed anyway. So that times 10 to the 3 minus that times 10 to the 3 divided by, I don't know. This could give me anything on this horrible calculator. Genuinely don't know if I'm typing this correctly, because, minus. They changed the input logic for these things, and I mean, that looks about right, actually, thinking about it. That looks about right. So 1,188. 1,188. Now I need the units. So that's going to be per, well, it's meters to the minus 3, kilograms to the minus 1. That is the unit of that. I don't make the rules, but there we go. That's the unit. Right, then I'm going to do the worst acceptable line of best fit. But first of all, let's do the intercept for this, which is going to be the value on the y-axis, which is, in this case, 11.09 times 10 to the 3, subtract the gradient times by the value on the x-axis, which is 970 times 10 to the negative 3. And that should equal the y-intercept. So I've just done y equals mx plus c, rearranged it, and then used the point with the highest values in order to calculate what the y-intercept will be. Because it's a false origin, I can't just read the y-intercept off the graph. And it gives me a y-intercept of 9937.6. Let's say 9938. 9938. And the units of this would be meters to the minus 3, because that's the unit. Right. Now the worst acceptable line of best fit. Gradient equals. And so we're going to use these points this time. So it's 10.93 subtract 10.20 times 10 to the 3 divided by 850 subtract 220 times 10 to the negative 3 is equal to, I always show you gradient calculations on the graph. I think that's a better way of doing it. Right, 10.93 times 10 to the power of 3 minus 10.2 times 10 to the power of 3, 850 times 10 to the power of negative 3 minus 220 times 10 to the power of negative 3. And that gives me a gradient of 1159. And that's in per cubic meter per kilograms. And then the intercept using that point is the same thing as before. So it's the y-axis value, 93 times 10 to the 3, minus the gradient multiplied by the x-axis value. So it's just y equals mx plus c, rearranged to make c the subject. 10.93 times 10 to the 3, subtract 1159 times 850 times 10 to the negative 3, and that gives me 9945 per cubic meter. So I've got a range there now, haven't I? And I can actually have an uncertainty in each of those. So my value of, and I'm going to have to do a lot of page turning now, 4g divided by pi d squared k is equal to, that's the gradient, so 1188 plus or minus, and that's going to be the difference between these gradients. So the absolute uncertainty in the gradient is going to be equal to, that's going to be the difference between these two. It's not going to be half the difference because the line of best fit should be the one down the middle. If I did the most extreme line of best fit that's most steep and line of best fit that's most shallow, then it'd be half the difference between the two. But I didn't do that. So it's going to be 1180 subtract 1159, 21. 21, and this is an absolute uncertainty. So this is going to be per cubic meter per kilogram. So this is 21, and this is per cubic meter per kilogram. And I'm going to do the same thing for the intercept. So that's going to be the difference between them. So that's 9938 subtract 9945. Oh, okay, that's going to be negative, but never mind, doesn't matter. 7. Let's say 7, and this is going to be per cubic meter. So my intercept is equal to 1 over K multiplied by atmospheric pressure. That's going to be equal to, there it is, 9938 plus or minus 7 per cubic meter. And now I've got enough to go on. I've got my value of D. In fact, I'm just going to write D again here. So my D is equal to 31.14 plus or minus 0.05, and that's in units of, well, let's say times 10 to the, what are they? Centimeter, millimeters, times 10 to the negative 3 meters. And of course, G, I'm going to go as 9.81 newtons per kilogram. Right, we've got all the pieces of the puzzle to calculate what PA, that's P subscript A, not PA the unit pascals, what PA is. Oh, that was a bad choice, wasn't it? Who decided to use PA for atmospheric pressure? What a wally. Right, whew, let's do this. First of all, let's calculate what K is. So K is going to equal 4 times 9.81 divided by pi, and also divided by 31.14 times 10 to the negative 3 squared. Calculator out. Running out of time. So anyway, 4 times 9.81 divided by pi. Where's my pi on this horrible calculator? The second function and that button. Weird. And then 31.4 times 10 to the power of minus 3 squared. I think that's input logic fine. Okay, I've got 12668. And the unit of that are going to be, oh, crumbs. Okay, let's see if we can work out the unit. Well, actually, unit of K is going to have to be Pascal cubic meters. So Pascal cubic meters, because it's a pressure multiplied by a volume. That's what it's got to be. So that saves me a bit of time trying to work out that. Or I guess Newton meters. Newton meters would also be the unit. Right, then I am going to calculate the uncertainty in K. So K, the percentage uncertainty in K is going to be the percentage, 2 times the percentage uncertainty in, where's the gradient? Oh, I haven't put the gradient in. Oh, mistake. K is equal to, if you were sitting there thinking, he's forgotten the gradient. Thank you. You are absolutely correct. Always worth following up on silly mistakes. Minus 3 squared, and then also divided by 1188. So divided by 1188, 10.66. And units of that are Pascal meters cubed, or Newton meters, I guess. Right, now the percentage uncertainty in K is going to be equal to the percentage 2 lots of the percentage uncertainty in D plus the percentage uncertainty in the gradient. Now, that's 2 lots of, what's the percentage uncertainty in D? 0.05 divided by 31.14 equals 0.16. 0.16%. I am presenting these as percentages, plus the percentage uncertainty in the gradient is going to be 21, I've got the gradient written somewhere, there it is, 21 divided by 1188. Oh, that's more like it, 1.8%. 1.8%. So 0.16 times 2 plus 1.8 is equal to. Now, you may be fussed about the rounding. I'm not, because I know I'm going to be rounding it all later anyway, so that should be fine. 2.1%. And then I can calculate what K is now. It's going to be 10.66 plus or minus. So let's divide that by 100 and times that by my 10.66. Plus or minus 0.23, and units are still Pascal cubic meters. Right, there's my K. Now I've got to do my calculation of this, of the atmospheric pressure. So atmospheric pressure is going to be equal to 9938 times 10.66. 9938 times 10.66, 105,900-ish pascals. Okay, not terrible. It's okay. Then I'm going to calculate the uncertainties. The percentage uncertainty in the atmospheric pressure is going to be the percentage uncertainty in K plus the percentage uncertainty in the intercept, which is going to be, percentage uncertainty in K is 23 divided by 1066. So it's about, I've already got that somewhere. There we are, look. Although that's slightly different, so maybe there's a rounding thing going on there. That's interesting. It's actually 2.2%. Well, we'll do 2.2% because apparently that's what it is. Plus the y-intercept uncertainty, which is going to be almost nothing. Look at that. 38. Yeah, I mean, that's nothing. Times by 100. That's giving me 0.070%. So that's 2.2%, two significant figures. And so our atmospheric pressure is going to be 2.2 divided by 100. There's my my percentage uncertainty as a relative uncertainty, 105,900 times, you have to press the times, the answer. Okay, so it is 105,900 plus or minus 2329.8, 2330. That's what I got there. And this is in pascals, but we don't write it like that. We only need a two significant figure. Right, yeah, so it would be 105,900 plus or minus 2300 pascals. That's how we would write it. And we could check atmospheric pressure and see whether it's within that range. So there we go. That's what we expected the atmospheric pressure to be. So, so confusing using PA as atmospheric pressure and PA as the unit of pressure. Hopefully you can see that's a subscript and that one's not. Okay, let's just check and see whether mine is in agreement. So 105,900 subtract 2300 is just outside that range. So close but no cigar. Close to measured value, but not within uncertainty. And of course, we can reference where this came from. Although I don't think you'd reference an app. I think you would have to actually look up a website of what this would be. But I'm going to reference for 𝗟's law. So I'm going to leave that as it is. And we're going to move now on to 𝗟's law. I believe the apostrophe comes after the S, not like what I wrote before. 𝗟's law. Now for 𝗟's law, we are looking at constant pressure. So this is saying that the volume of a gas is equal to some constant multiplied by the absolute temperature of the gas if the pressure and the amount of gas are constant. So this should be much more straightforward to analyze because I should just be able to measure volume of gas and temperature of gas. And it turns out I've got a nifty little piece of kit that's going to help me with this. So here it is. It is just a capillary tube. It's just a tube that's open at one end, open to the atmosphere. So this will be atmospheric pressure for the air that's exposed to the outside. There's then a little bit of oil here, which is separating the air that's outside, the great outdoors, from the air that's on the inside, because at the bottom of this it's sealed. And all the way up this side is a scale. Now there may well be a systematic error in the volume that this scale tells me, but this scale is a length scale. And if the diameter of the capillary through this tube is the same, then the length is proportional to the volume. Now, I don't know what that constant K is going to be, because it's obviously going to depend on the diameter of this. There's no way I can measure the diameter of this capillary tube. But I can ignore that, because actually all I'm interested in this experiment is determining absolute zero. As we change the temperature of the air that's trapped between the sealed end and the oil, the volume of that air will change. If I drop the temperature, that volume will reduce. If I increase the temperature, that volume will increase. And the volume being proportional to the length means that all I have to do is extrapolate my results back to when the length is zero. When the length is zero, that should happen when the temperature is absolute zero, because volume is proportional to temperature. But it's not perfect because we've got this systematic error. So maybe I'll be able to include that in my analysis somewhere. To measure the temperature, we're going to use a thermometer, which is going to give me the temperature in Celsius. And to change the temperature of the gas, what we're going to do is stick the whole apparatus in a beaker and pour water in the beaker. And try to make sure as much of that gas as possible is immersed in the water. And we're going to use boiling water and cool the water bit by adding cold water to it. Measuring the temperature and measuring the length of the capillary. And that's going to be our experiment. So just while the water in the kettle is boiling, this is the kettle here, I've got a beaker of cold water, and I'm going to choose the water temperature in this water bath by mixing the cold and warm water. But I have a data point already here, don't I? Because I have the air in this room is at 16 degrees Celsius, and the column going from the bottom of where the red mark is on this instrument here, the column is at 16.2. So I'm going to put 16.2 centimeters and 16, I think it was, yes, 16 degrees Celsius. And I've drawn my table up like that. And I am just using temperature in degrees Celsius, and I'll fiddle around with that later. Right, let's add some boiling water. Pour it straight in, doesn't matter if the beaker smashes and boiling water pours on my lap. Shouldn't happen, of course, because it's a borosilicate beaker. Already we can see, you might not be able to see on the camera, but the thermometer is reading a much higher temperature, and I'm watching the gas bubble that's trapped, the trapped gas, increase in volume. Now that volume of gas is going to extend outside the water, but gas is not a very good conductor of heat, so the fact that the gas is outside isn't really going to matter, and convection within that tube should make sure that it's all the same equilibrium temperature eventually. I mean, it won't be perfect, but when everything stops moving, I'll make my measurements. Just turn the thermometer around a bit to help me make my measurements. Has that stopped moving? I think that's still moving a little bit. So we just have to wait now. It's a fun task. Just wait until the red line stops moving. And I think that's the case. So that's 90 degrees Celsius, and that is 19.7, centimeters. So 19.7 at 90 degrees Celsius. Then I need a new water bath. So I need to tip out some of the boiling water and add some cold water. Of course, the beaker is now exceptionally hot. This was the wrong way around altogether, wasn't it? I should probably use some sort of gloves or something to help me so I don't scold myself. But sure, it'll be fine. Ow, 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 ow. There we go. Perhaps start cold and add boiling water in stages rather than doing what I did, because in terms of competency 3, lab safety, that perhaps wasn't the best thing to do. Right, add a bit of cold, just like that. And then I needed to reach an equilibrium temperature, so I should have some sort of stirrer. I'm not a chemist, I'm just going to use this piece of equipment to do a bit of stirring. It'll do the job. Now this thing has a metal ruler. I'm not actually using the scale on the metal ruler. Don't use a plastic ruler, because when you pour boiling water on one of those polythene or polycarbonate, polythene, I don't know what they're made out of, rulers, actually they will deform. So let's move this closer so you can see what I'm doing. I'm now waiting for the temperature to reach an equilibrium and for the gas volume to stop moving. If I insulate this beaker, then it will keep the same temperature for longer, and that could potentially mean I get better results, but I don't care. So 66 degrees Celsius and 18.8. 18.8 and 66. 18.8, 66. Writing the numbers down. Right, let's do it again. Take that out. Pour out some of the hot. It's now not quite as bad as it was. Add some cold. See, this practical takes very little time to do. Once you've got it understood what you're doing, it's very, very straightforward. Give it a bit of a stir, and then we wait again. I'm going to take 7 results, and I am going to incorporate into my results the 0 error on the length measurement. And the fact that length is proportional to the volume of the air inside the capillary tube, I'm just going to work with length. So 55 degrees Celsius, 18.3, 55, 18.3, 18.3, 55. Let's drop the temperature down again. And it's actually quite remarkable how quickly the gas volume stops changing. You don't want to wait too long because, as I say, there's heat radiating out of this all the time, and what will end up happening is you're watching something move very slowly, wondering when to take a measurement, and it's moving very slowly because the temperature of the water bath is changing. So where are we up to? Temperature still dropping. I'm just watching those two. Move it closer. I'm just watching the red line on the thermometer and the red bead here, and deciding when they stop moving. I reckon that's 43 degrees Celsius and 17.8. 43, 17.8. All right, let's go again. What you can do, of course, is you can actually use ice and water as well to get a lower value. I might have tipped out a bit too much hot that time. Let's put the kettle back on in case I want to add some more hot. Yeah, but you can do that. You can add ice and water to drop the temperature down even lower. Now I'm using oil in here because my physics technician, who is absolutely wonderful, did a bit of reading and found that this is quite a good way of doing it. Instructions tend to say to use a very concentrated acid. I can't remember if it's hydrochloric or sulfuric acid, but some very concentrated acid, because the boiling point of the acid is much higher than the boiling point of water, but also because the acid being very concentrated, any moisture that's in the air is going to diffuse into that acid. It will dry the air out. And for an ideal gas, you want it to be very dry air, which is fine. So that's 29 degrees C and 17.2. 29, 17.2. However, I've got one more reading to take, so I might not need the kettle. However, I think that using some sort of concentrated acid in the lab should be avoided when possible. And, oh, right, let's add a bit of this then. Don't know what temperature that's going to be. Yeah, I think it should be avoided when possible because of the safety implications of using a concentrated acid. The second thing I would say is we could use water. And I've seen it done, and I've done it with water myself, and it works okay, where you get a little bit of water in here. The downside to that is that, first of all, the air won't be dry. Results are still okay, but they're not quite as good. The second problem with that is that if you are using water in here, then you can't increase the water bath temperature too high because the water will evaporate more quickly because the boiling point of water is only 100. So you tend to have to go from about 60 degrees Celsius down and add ice to get down to 0 degrees Celsius as your temperature range. As this is, I'm able to get a temperature range of, what is it, 90, 80, 70, about 70 degrees Celsius, 60-something degrees Celsius, which is pretty good. Right, 37, 17.5, 37, 17.5. And that's it. I've got all the data I need written in my book. Hopefully that will be okay. Notice that my temperature has been measured to the nearest degree Celsius because the resolution of my instrument was degrees Celsius. I didn't try to interpolate between those. No matter what they tell you in the other sciences, it's wrong. And the length of the column is in centimeters. So let's move the camera around and we'll do some analysis. Okay, camera's moved. So remember what we said up here, the volume is that. And as we know, the volume is equal to the area of the interior of the capillary tube, the cross-sectional area, multiplied by the length. And actually, it's multiplied by the length plus this extra bit of length, which is our systematic error, our zero error in that length. And this is the measured length. A is obviously the area. And V is the volume. Well, let's substitute that in and then take the area, which is constant, and absorb it into the other constant. We end up with L plus L is equal to K multiplied by T, where T is the temperature. Just like that. Now I could take all these temperatures and turn them into Kelvin temperatures. I could do that. However, I don't really need to do that because that temperature is just going to be the Kelvin temperature, which is what I'm trying to, the Celsius temperature, which is these, and then add some number. And that number is going to be the number of temperature. Maybe I should call that T and then 0. Let's use a different symbol, T0, where T is the temperature in Kelvin of 0 degrees Celsius. So you know what I'm trying to say there. But all we've done there is shift the x-axis. That's all that's done. Now, because of this term, because of this zero error, which is there on this capillary tube, I'll show you again. Let's just dry it a little bit. I'll show you again at the very bottom. I'm not sure if you can see this. Maybe if I can zoom in a little bit. Let's see if I can zoom in. You can see that there is a volume at the bottom before the numbers start. You can see that, hopefully. Now, because of that, we can't, let's just zoom back out to there. we can't actually determine absolute zero. And I'll show you why. We can get close to it, but we can't determine it. So we take this equation here, and we can say that, well, let's multiply the k out. So L plus this zero error is equal to k theta temperature plus, and then it would be k, and then the temperature in Kelvin, that's 0 degrees Celsius, right? Which is what would be adding to all of those to get to Kelvin temperature, which is what's proportional to the volume. So there's my expression there, and then I can subtract the absolute, the zero error. So the absolute uncertainty is the zero error in this case, a systematic error. Doesn't matter. I'll subtract the zero error from both sides, and I get k theta plus kt0 minus L. And of course, this bit in brackets is the y-intercept. If I plot this on the y-axis, and I plot this on the x-axis, just like that, then this is going to be the gradient, which I will be able to measure, and all of this will be the y-intercept. And that's the problem, because how do I determine T0, from which I'd find out absolute zero? You know, that's easy enough to do. If T0 is how much I have to add to absolute zero to get 0 degrees Celsius, then T0 in degrees Celsius, well, absolute zero is just going to be the minus T0. But I don't know what that is. Now, I could say, well, I know absolute zero, and correct all these to turn them into Kelvin temperature, and then do the analysis. But then it's assuming I already know absolute zero. And the whole point of this investigation is to determine absolute zero. So the problem is this pesky thing here, this value here, and we don't know what that is. However, what we can do is see what this value is for the y-intercept, and say, well, if L equals 0, what is T0? And then see what happens with slightly different L's and see what the relationship is there. We'll do that. So let's do the graph, and we'll see what happens. I'm just thinking out loud, of course. A lot of times the notes on this always say, well, you can easily find absolute zero by just plotting this versus this. It's not actually as simple as that because of that zero error on the capillary tube. So there's no point having a real origin. We might as well have a false origin looking at these data, which hopefully you can see on the edge of the screen. So we're going to go from about 16 to, let's say, 18, and that's going to be on the y-axis. So 16.1, 2, 3, 4, 5, 6, 7, 8, 9, 17.1, 2, 3. That's not going to work. So 16.2468, 17.2468, 18.246. That would work. Oh, it goes up to 20, 16 to 20. Sorry, I didn't look properly. So 16.5, 17.5, 18.5, 19.5, 20. That would occupy just under half the page, but it would be the most sensible scale. So it looks like we're doing that. And we can write the scale down. Sometimes I find it helpful to write the scale down, but I think at the moment I'm going to try and just remember that every big square is 0.5 of a centimeter. And then on the horizontal axis, so that's going to be our temperature. It goes from, again, 16, but this time 16 to 90. So let's say 15 to 90. So 15, 20, 25, 30, 35, 40, 45, 50, 55, 60 doesn't fit. So let's go from 10, 20, 30, 40, 50, 60, 70, 80, 90. That does fit. And we can go right to the edge then. So you're going to do this. So you can see how I worked out the scale in real time so you could see what I was doing. This is 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50, 60, 70, 80, 90. Oh, I hope it's recording sound. Then I'm going to label this the temperature in degrees Celsius. Then on the y-axis, remember, it was 0.5 centimeters per big square. So we were going from 16, 16.5, 17, 17.5, 18, 18.5, 19, 19.5, up like that. And I think that's about as good a scale as I'm going to get. I think it's just about half of it. I wonder if I can extend it a bit further. 16. No, because we don't want to do any other intervals. We don't want to do 0.25 intervals, really. 16.2468, 17.2468, 18.246, no. So 16.5, it's going to be the best we can do. So let's have that as 16.0, 16.5, 17.0, 17.5, 18.0, 18.5, 19.0, 19.5, 20.0. And notice I'm matching the decimal places on my table, which indicates the resolution of my instrument, to the decimal places on the scale here, which is what you should be doing. Right, this is length in centimeters, not that it matters. All right, okay, let's plot some points. So 16, you don't need to watch me do this, you can skip forward. 16.2, so that's 1, 2, there we go. And then 19.7, wow, that's all the way up here. And 90, that's there. Oops. I haven't thought about uncertainties in this, have I? But I didn't do in repeats, because you can't really do repeats for this. Right, 18.8. 18.8, so dun, 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 that's there. And 66. 55, 66, that's there. Hey, that's looking pretty straight so far. Nice. 18.3. 3 is going to be there. And 55. That's looking very straight. 17.8. Be there. And 43. Nice. 17.2. Be there. And 29. Yeah, there's a bit of a curve on it, but okay. 17.5. Oh, I did this in a really odd order, didn't I? And then 37. Okay. Not quite as straight as I wanted. That bit looks pretty straight, but it looks like it curves at the bottom there. Now, obviously, that point here has had longer to reach an equilibrium temperature. These didn't have very long to reach that equilibrium temperature, and yet they look like they're in a nicer straight line than that point is. So what does that tell me? That tells me that perhaps I should have waited longer, but of course the longer I wait, the more the temperature of the water bath drops. But I could have insulated the water bath to make those results better. Never mind, I'm going to use the straight part of my graph and we'll see how it goes. So this is the analysis part. And I'm going to just put it so that there's as many points either side of the line, but obviously I'm discarding this anomalous result here, which I'm going to label discarded anomalous measurement. Maybe I shouldn't have done, maybe I should have gone steeper like this. And maybe I could actually not discard it and do a line of best fit including it and see if I've got an uncertainty between those two. So if I do that, let's change color for this just for the fun of it. Let's include that point for a second and see what the results would look like then. So I'm going to say for line of best fit, and we've got in black the line of best fit, and in green we've got the worst acceptable line of best fit, where I choose not to discard that, and perhaps even that should be pushed up a little bit more, but okay. There, it'll give us some idea. I'm going to reference it and see how bad it looks later. Okay, usual method of determining gradients, which I will need to work out the intercept. That's a nice point there. And looking at the top here, difficult to see because that green line is quite close. That's a good point there. So I've chosen 2 points, zoom in a bit maybe. I've chosen 2 points where the grid lines cross the line of best fit. Okay, now I'm going to label my coordinates. So this one is 12, and then it's 16.45. And this one up here is 71, and it's 18.95. And I'll do the same thing for the worst acceptable line of best fit, whereas it goes through some nice grid lines. There, looks like it's good. So that is 18 and 16.1, 2, 3, 16.35. And up here somewhere, there, got close to that, but that's okay, 72, and it's the same, 18.95. So you might not be able to see that green on the background, but I've recorded those data points. Right, so line of best fit gradient is going to be, we're showing the full calculation, let's do an equal sign. We're going to show the full calculation. So 18.95 subtract 16.45 divided by 71 subtract 12, and oh, I need my horrible calculator. Wait a minute. Here it is. Yuck, 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 yuck. 18.95 subtract 16.45, 71 subtract 12. Give it to me in standard form. How do I get standard form? No, it's not in there. Setup, input, output, maybe. No, setup, number format, psi. Give me loads of significant. Oh, for goodness sake. That didn't work. Setup, fraction result. I don't want a fraction. Setup, number format. I thought I'd done that. Psi 9. Well, that's not standard form. Oh, horrible thing. All right, let's have math in, decimal out. Right, there we go, standard form. Ah, stupid calculator. Anyway, 4.2. Let's go 4 significant figures because there's always, there's no harm in having too many. And the unit is going to be centimetre per degree Celsius. Centimetre degrees Celsius to the -1. Just made it fit in there right in the crease of the page, but there we go. Right, that's the line of best fit gradient. Then we want the intercept. And that is going to be using this point here. So it's going to be the y value. So that's 18.95, subtract the gradient, 7 times 10 to the -2, multiplied by the x value, 71. And that's going to give me, so 18.95, subtract the answer from the previous one times 71 equals, okay, so 15.94, and that will be in centimeters. And remember what that y-intercept represents. It is this term down here. So physical significance of that, difficult to unpick at the moment. Now we're going to do the same thing for the worst acceptable line of best fit in order to get our uncertainties. So gradient is going to be 18.95 subtract 16.35 divided by 72 subtract 18. So 18.9, forgot to press the fraction first. How can anyone think this is a better calculator than a reverse Polish notation calculator? 4.815 times 10 to the negative 2 centimeters per degree Celsius. And the intercept is going to be the y-axis value. Let's go with 18.95. Subtract the gradient, multiplied by the x-axis value. And that's going to be 18.95, subtract the answer times 72, 15.48 centimeters. So now I've got the data I need up here from the graph. I'm now going to go back over here and see if I can make sense of it. Oh, I suppose I better work out the uncertainty. So we're going to say gradient is going to equal, therefore, 4.237 plus or minus, let's just work it out. So it's going to be a difference between these two. So 4.815 minus 4.237, it's all got the same power, 0.578. And obviously we would have to round away that last digit because we want two significant figure uncertainties, times 10 to the negative 2 centimeters per degree Celsius. And the intercept is going to be the same thing. It's going to be 15.94 plus or minus, and let's go 15.94 subtract 15.48, 0.46. So I wouldn't have to do anything to that. That's fine. So now I've got my two important values here that I'm going to put into this equation here. So we know that kt0 minus L is equal to 15.94 plus or minus 0.46. And actually, we can even say that k, so we can say 4.237 plus or minus 0.578 times 10 to the negative 2 multiplied by t0 minus L is equal to 15.94 plus or minus 0.46. Fine. Now, what you can do at this stage, what could we do at this stage? We could do the whole experiment again with a different capillary tube, actually, and with a different systematic uncertainty. Then we'd have two simultaneous equations that we can combine to calculate the two L's. Once we've got the two L's, we can get that. What I'm going to do is just say, look, let's say L is equal to 0. I mean, it's not, and let's estimate what L is, rather than do the whole experiment again with a different tube. And looking at it, I'm estimating that L is going to be, give or take, let's say between 2 and 3 millimeters. It's between 2 and 3 millimeters. So let's say L is equal to, let's say 2 plus or minus 1. That's going to be a huge uncertainty, isn't it? Yikes. Millimeters. 50% uncertainty. So when I combine uncertainties, but that's going to give me 50% uncertainty on my final answer. Well, no, because we're adding it. So we're going to be adding absolute uncertainty. So, okay, it's not quite so bad. Right, let's, I've got to turn the page now. Nuisance, and I've got water on this page. Right, let's turn the page. I'm actually going to write all this again, just so I can keep track of what the hell's going on. So 4.237, 4.237 plus or minus 0.578 times 10 to the minus 2 multiplied by t0 minus, I reckon, 2 plus or minus 1, but that's in millimeters. So because everything else is in centimeters that I've used, that's going to be 10 to the minus 1. Got to be careful with that. Oops, make it so you can see it. And then this last one there, 15.94 equals 15.94 plus or minus 0.46. 0.46. There we go. One unknown, but I have a horrible estimate of that. So let's add this term to both sides. So we get T0 is going to equal 15.94 plus or minus 0.46 plus this term, so 0.2 plus or minus 0.1, I'm going to put it into centimeters, divided by 4.237 plus or minus 0.578 times 10 to the negative 2. And that will be in degrees Celsius. But remember that 0 degrees Celsius is the freezing point of water. So we're hoping that T0 is going to be about 273. That's the temperature in Kelvin equivalent to 0 degrees Celsius. We're hoping that's 273. So first of all, let's just check. So that's going to be the mean T0 is going to be 15.94 plus 0.2 divided by 4.237 times 10 to the negative 2. We'll do the uncertainties in a second. So that's 15.94 plus 0.2. Oh, I have to press the fraction button first. Listen, I know it gets boring listening to me moan about calculators, but, you know, tough. 381. Wow. 380.93 degrees Celsius. That's the temperature. Kelvin. Kelvin. That is the temperature of the freezing point of water, apparently. Well, it's a bit wrong, but maybe when we deal with the uncertainties, it'll work out to be within tolerance. So we're going to first of all say that the uncertainty in the top part of this, the uncertainty in the 15.94 plus 0.2 part is going to be equal to 0.46 plus 0.1 equals 0.56. And the unit of that is going to be, I don't even know what the unit of that is. It's going to be the centimetre. And then we've got the percentage uncertainty in that term, plus 0.2. I usually use symbols at the top, but there we go. So that's going to be 0.56 divided by this stuff here, 15.94 plus 0.2. We didn't need to use a calculator for that. So about 3.47. Let's say 3.47%. Just because I rounded that digit there. And that's going to be added to the percentage uncertainty in the 4.237 times 10 to the negative 2, which is 0.578 divided by 4.237. Wow, it's even higher. So that's 13.6%. 13.64%. So the uncertainty in our measurement of the Kelvin temperature of the freezing point of water is going to be 13.64% plus 3.47%, which is going to be equal to 3.47 plus that. No. So 13.64, I forgot the percentage signs, 3.47. 17.1%. So 17%. Yeah, that's not going to be within tolerance, is it? So what is that? Let's go answer divided by 100 to get it there and multiply it by 380.93. So that gives me 65. So our actual answer, T0, is 380.93 plus or minus 65.18 Kelvin, which of course we're going to use two significant figure uncertainties, so 381 plus or minus 65 Kelvin. Well, when we look it up, it's supposed to be, expected value for freezing point of water is supposed to be equal to 273-ish Kelvin. And that is way outside tolerance. So this experiment has not been a huge success, but there we go. This value is not within uncertainty of measured value. It's as simple as that. Now, if I didn't include that term, this would be a touch lower. So I wonder what it would be if I didn't include that zero error. Not that it would matter, but I'm just curious to see. So 15.94 divided by 4.237 times 10 to the power of -2. 376. It'd be a touch lower. 376, still going to be outside tolerance. So the zero error wasn't correcting for the zero error in the length wasn't the issue at all. It was the right thing to do. Well, maybe I've measured a new absolute zero. Maybe actually we've been wrong all along. That's unlikely. More likely that I didn't wait long enough when I did my measurements of the length of the capillary. Or maybe because part of the air column is outside the water bath. Or there's all sorts of things that could have gone wrong. But I'll leave it there, actually. I think that's fine. Sometimes your results work well, sometimes they don't. On this occasion, they've not worked brilliantly. Atmospheric pressure was a little bit outside what it should have been, just a little bit. And absolute zero was a little bit outside of what it should have been, just a little bit. But again, I've not actually measured absolute zero. I've measured the temperature in Kelvin at the freezing point of water, but that's absolute zero. From that, you can work out absolute zero. Okay, I'll stop there. Now, I hope you found that a useful practical to see. And as I say, it's important to do the error analysis on everything you do. But sometimes, even when you do the error analysis, the results still don't quite work out as they should be. And then the challenge is to figure out what's gone wrong. Enjoy.